Our universe is built on secrets we cannot see. Behind every star, within every atom, lies an invisible architecture of hidden fields. These are not places you can visit. They are the universe's fundamental scaffolding, the silent rules that dictate how particles gain mass, why space itself is expanding, and what might bind all of reality together. By the end of this journey, you will have explored 30 distinct theories about these hidden fields, from the scientifically confirmed to the philosophically profound. We will ask, what gives our world substance, and if empty space is truly empty? We will examine forces that might rewrite gravity and fields that could explain consciousness itself. What invisible layer of reality intrigues you the most? The first and most famous of these hidden fields is one we have actually seen. Not the field itself, which is everywhere, but its signature ripple. This is the Higgs field, the universe's most fundamental property manager. Its sole purpose is to give particles their mass. Without it, every fundamental particle would zip around at the speed of light, weightless and unable to form atoms, stars, or us. Think of the Higgs field not as empty space, but as a uniform, invisible substance that fills the cosmos. Some particles, like photons, glide through it effortlessly, feeling no drag and thus having no mass. Others, like electrons and quarks, interact with it strongly. They wade through this cosmic molasses, and that resistance is what we experience as their mass. The more a particle interacts with the Higgs field, the heavier it becomes. To prove this elegant idea was not just mathematics, scientists needed to find a disturbance in the field. Just as shaking a mattress creates a wave, they needed to create a ripple in the Higgs field itself. That ripple is the Higgs boson. After decades of searching, it was finally detected in 2012 by the colossal Large Hadron Collider, a machine that smashes protons together at nearly the speed of light to recreate conditions from the universe's first moments. That discovery was monumental. It confirmed the final piece of the standard model of particle physics, our best map of the subatomic world. The Higgs field is the cornerstone. It explains the origin of mass for fundamental particles, which is the first step in building everything we see, but it also raises a deeper mystery. Why does the Higgs field have the strength it does? The value it holds seems improbably fine-tuned for life to exist. This question of why the field is just so opens the door to all the other, more speculative fields we will explore. Yet if the Higgs field gives particles their substance, what about the space between them? So the answer shatters our classical intuition. Empty space is not empty. It is not a void. It is a vibrant, humming medium, alive with potential. This is the realm of quantum fields, the true bedrock of reality. Forget thinking of the universe as a collection of tiny billiard balls. Instead, picture an infinite, interconnected ocean of invisible fields. There is an electron field, a quark field, a photon field, and more. Every type of particle is just a localized excitation, a tiny wave or ripple in its corresponding field. What we perceive as an electron is a brief knot of energy in the universal electron field. A photon is a vibration in the electromagnetic field. Particles are not permanent objects. They are temporary events, and in the quietest places, where no particles seem to exist, these fields are never still. They undergo constant, frantic fluctuations. This is the quantum vacuum. Think of it as a calm sea on a windless day. From a distance, the surface looks flat and serene. But up close, you see it is constantly shimmering with tiny waves that form and vanish in an instant. In the quantum vacuum, these are virtual particle pairs. A particle and its antipartner can spontaneously blink into existence, borrowing energy from the vacuum, itself only to annihilate each other and vanish a moment later. This is not a theory. We can measure its effects. One stunning demonstration is the Casimir effect. Take two perfectly smooth, uncharged metal plates and place them incredibly close together in a vacuum. Classically, nothing should happen. But in the quantum world, something remarkable occurs. The space between the plates is so narrow that only certain wavelengths of virtual particles can fit. Outside the plates, all wavelengths can fluctuate freely. This creates a subtle pressure difference, and the plates are pushed together by the sheer energy of the vacuum itself. It is as if the silent hum of empty space has a physical force. This background energy is called zero-point energy, and it implies that even at absolute zero, the coldest temperature possible, the fields of the universe would still be quivering with this fundamental activity. So the stage is set. Fields are not just a convenient mathematical tool. They are the primary substance. Particles are secondary, fleeting manifestations. This quantum field theory view transforms our entire perspective. Reality is a dynamic, interactive tapestry of fields, and if that is true, then what other fields, beyond those we have catalogued, might be woven into that fabric, quietly shaping the cosmos in ways we have yet to perceive? But if the quantum vacuum is this sea of constant potential, what force could have stirred it into the vast cosmos we see today? This leads us to a field so powerful it may have written the opening chapter of the universe in a single, breathtaking instant. This is the inflaton field. In the earliest moments, far less than a second after the Big Bang, our entire observable universe was smaller than a single atom. According to the theory of cosmic inflation, a strange and potent field, the inflaton field, suddenly dominated reality. Picture this not as an explosion, but as a phase change, like water flashing into steam. Inflaton field entered a state of unstable, high energy, and this energy did something extraordinary. It caused space itself to expand at an exponential, faster-than-light rate. In a time span so short it defies human comprehension, a subatomic speck of reality ballooned to become larger than our entire galactic horizon. Then, just as suddenly, the field decayed. That immense stored energy was released, flooding the newborn universe with the hot, dense plasma of particles that would eventually become everything. This idea solves profound puzzles about our cosmos. The first is the horizon problem. Look at the cosmic microwave background, the ancient afterglow of the Big Bang. Its temperature is uniform across the sky to 1 part in 100,000. But in the standard Big Bang model, these distant regions should never have been in contact to equalize their temperature. Inflation fixes this. It says that before inflation, the entire observable universe was a tiny, connected region that had time to reach a uniform temperature. Then inflation stretched it to cosmic scales, preserving that perfect smoothness. The second puzzle is flatness. On the largest scales, the geometry of our universe appears remarkably flat, not curved. For this to be true after billions of years of evolution, the initial conditions had to be fine-tuned to an absurd degree. Inflation naturally produces this flatness. Imagine blowing up a balloon to an immense size. Any small wrinkles or curves on its surface, when it was tiny, become imperceptibly smooth and flat as it expands. Inflation did that to space itself. Furthermore, as the inflaton field decayed, its energy fluctuations were imprinted as tiny density variations in the early plasma. These microscopic seeds, stretched across the cosmos by inflation, became the gravitational blueprints for all future structure. Every galaxy, every cluster, every filament in the cosmic web owes its origin to those quantum ripples in the inflaton field. The evidence for this is written in the cosmic microwave background. Satellite missions have mapped its faint temperature differences, and the pattern matches the predictions of inflationary theory with stunning precision. So while we have not detected the inflatant particle directly, its signature is etched across the sky, a fossil of that first unimaginable expansion. The inflaton field presents a compelling story, but it leaves a critical question unanswered. What ended inflation? What made that immense field decay and release its energy to create our universe? The answer might lie in another, even more mysterious field. That immense energy from the inflaton field had to go somewhere, and it became the fiery birth of matter and radiation. But billions of years later, a new mystery emerged. The expansion of the universe, which everyone expected to be slowing down due to gravity's pull, was found to be speeding up. Something was acting against gravity on the largest scales, a repulsive force woven into the fabric of space itself. We call this phenomenon dark energy. The simplest explanation is the cosmological constant, an idea Albert Einstein introduced and later called his greatest blunder. It treats dark energy as a fixed property of empty space, a constant energy density that never changes. As the universe expands and more space comes into existence, the total amount of this repulsive energy grows, driving the acceleration faster and faster. It is elegant, but it feels like a placeholder. It tells us what dark energy does, but not what it is. This is where a more dynamic theory enters, one that imagines dark energy not as a static feature, but as another hidden field in action. This theory is called quintessence. Picture quintessence not as a constant, but as a fluid. Imagine a vast, invisible substance permeating all of space. But unlike the Higgs field, this substance can thin out or become denser over cosmic time. In physics terms, it is a rolling, scalar field. Think of a ball resting on a gentle, sloping hillside. The ball's position represents the field's value, and the slope of the hill represents its potential energy. In the early universe, the ball might have been high on the slope, rolling slowly. Its energy density was high, but it was masked by the even greater density of radiation and matter. As the universe expanded and matter diluted, the ball continued its slow roll downhill. Today, we are at a point where the ball's energy, the energy of the quintessence field, has become the dominant component in the cosmos. Its gentle pressure is what pushes space apart. The crucial difference from a cosmological constant is that this field evolves. Its energy density can change over time. It could slowly decrease, increase, or even oscillate. This opens a profound set of possibilities for the ultimate fate of everything. If quintessence weakens over time, the acceleration of the universe might eventually slow or even reverse. If it strengthens, the acceleration could become unimaginably violent, leading to a future where the expansion rips apart galaxies, stars, and even the fabric of space-time itself, in the event cosmologists call the Big Rip. The quest to distinguish between a simple constant and a dynamic field like quintessence is one of the greatest challenges in modern cosmology. By measuring the expansion history of the universe with exquisite precision, by observing distant supernovae and the large-scale structure of galaxies, astronomers are trying to detect any subtle change in the strength of dark energy over billions of years. Is the push against gravity perfectly steady, or is it subtly shifting? The answer lies in the behavior of a field we cannot see, one that holds the blueprint for how our story ends. The fate of the cosmos may be tied to a field we cannot see, but what about the very fabric of matter itself? There is a strange asymmetry in one of nature's strongest forces that suggests another hidden player. This is the mystery of the strong CP problem, and its most elegant solution points to a new field and its particle, the axion. To understand why, we need to look at the force that binds atomic nuclei together, the strong nuclear force. It is described by a theory called quantum chromodynamics. This force should, in principle, allow for a certain kind of asymmetry, a difference in how it treats particles and their mirror images, combined with a charge reversal. Physicists label this combined effect CP violation. We see a tiny amount of it in the weak nuclear force, which is why our universe is made of matter and not antimatter. But according to the mathematics, The strong force should exhibit this CP violation as well, and to a degree that would make atoms unstable. In reality, it does not. The strong force appears perfectly symmetric. The measured violation is 0 to an incredible precision. This is not just a minor detail, it is a glaring fine-tuning problem, as if a fundamental dial in the laws of physics has been set exactly to 0 for no apparent reason. In the late 1970s, physicists Roberto Peccei and Helen Quinn proposed a brilliant way out. They suggested a new, fundamental symmetry in nature, one that is spontaneously broken. When this symmetry breaks, it gives rise to a new field filling the universe, the Peccei-Quinn field. And just as ripples in the Higgs field give us the Higgs boson, oscillations in this new field would produce a new ultralight particle, the axion. The beauty of this idea is that the axion field would naturally settle into a state where it cancels out that troublesome CP violation, solving the problem elegantly. But the implications go far beyond nuclear physics. The axion, if it exists, would have just the right properties to be something else we have been desperately searching for: cold dark matter. It would be electrically neutral, incredibly light, and produced in vast numbers in the early universe. These particles would be ghosts, streaming through you and everything around you at every moment, interacting so weakly with ordinary matter that they are virtually undetectable. This is why experiments to find them are exercises in extreme sensitivity. The most famous is the Axion Dark Matter Experiment, or ADMX. It uses a powerful superconducting magnet to create a strong magnetic field. The theory predicts that in the presence of such a field, an axion could very rarely convert into a microwave photon. The experiment is essentially a giant, ultra-cold radio receiver, tuned to scan through millions of possible frequencies, listening for the faint whisper of an axion converting into a photon inside its resonant cavity. It is like trying to hear a single, specific note played by a single violin in a symphony orchestra that is playing every possible note at once, from miles away. The hunt for the axion is a testament to our ingenuity, searching for a particle born from a theoretical necessity that might also hold the galaxies together. It connects the infinitesimally small puzzle of nuclear symmetry to the cosmic scale of dark matter, suggesting that one subtle field could answer two of the universe's deepest questions at once. The axion is a ghost that might hide in plain sight, but some theories propose a field that is actively hiding from us. This is the chameleon field, a hypothetical component of dark energy with a truly bizarre property. It changes its behavior based on its surroundings, like a cosmic chameleon blending into the background. The core idea is simple yet profound. This field's effective mass, and therefore its strength, depends on the local density of matter. In the near-perfect vacuum of interstellar space, where matter is sparse, the chameleon field would be very light and long-ranged. Its repulsive force could stretch across vast cosmic distances, contributing to the accelerated expansion of the universe. But bring it into a dense environment like a laboratory on Earth, or even within our solar system, and the field becomes incredibly heavy and short-ranged. Its influence shrinks to a microscopic scale, effectively hiding from our most sensitive instruments. This is why it has evaded detection. Think of it like a sound wave. In the open air, a low note can travel for miles. But inside a dense, soundproofed room, that same vibration is absorbed almost instantly, unable to propagate. The chameleon field does something similar with its force. In empty space, it whispers across the cosmos. In a lab, it falls silent. This behavior is not just a convenient trick to avoid being found. It is a direct challenge to one of the most successful theories in all of science, Einstein's theory of general relativity. For over a century, general relativity has perfectly described gravity as the curvature of space-time by mass and energy. It predicted black holes, gravitational lensing, and the expansion of the universe itself. Yet it cannot explain dark energy without adding an extra term, the cosmological constant, which feels like an arbitrary fix. The chameleon field, and theories like it known as modified gravity, attempt to rewrite the rules from the ground up. They suggest that Einstein's equations are not the final word on large scales. Perhaps gravity itself behaves differently in the low-density emptiness between galaxies than it does in our high-density neighborhood. The chameleon is a specific proposal for how that modification could work, a new field that mediates a fifth force, one that masquerades as dark energy in the void, but cloaks itself where we live. Testing this requires extraordinary ingenuity. Scientists are designing experiments that probe gravity at incredibly small distances, searching for any deviation from Newton's familiar inverse square law. They use exquisitely balanced torsion balances or microscopic cantilevers in high vacuum chambers, looking for an extra whisper of force between test masses. Others look to the cosmos, studying the motions of stars within dwarf galaxies or the subtle distortions of light from distant galaxies, searching for signatures that gravity's strength varies with the environment. Finding the chameleon would be a revolution. It would mean that the force shaping the entire cosmos is not a mysterious, constant energy in space, but a dynamic and cunning field that has been eluding us by design. It would show that the laws of physics are not universal in the way we thought, but are context-dependent, changing their tune based on the density of the stage. A chameleon field hides its nature, but some fields have revealed theirs through a cosmic act of transformation. This is the principle of symmetry breaking, where a hidden field changes state and in doing so defines the very laws of physics we experience. The first and most crucial example already lives in our story. The Higgs field is not just a giver of mass. It is the agent of electroweak symmetry breaking. In the universe's first searing moments, when temperatures were beyond imagination, two of nature's four fundamental forces were not separate at all. Electromagnetism, which gives us light and chemistry, and the weak nuclear force, responsible for radioactive decay, were perfectly unified into a single electroweak force. They were symmetric, indistinguishable, and the Higgs field was in a state of perfect, symmetric zero. Then, as the cosmos expanded and cooled, something profound happened. The Higgs field underwent a phase transition. Think of it like water freezing into ice. In the liquid phase, every direction is the same, symmetric. But when it freezes, the water molecules lock into a crystal lattice, picking a specific orientation and breaking that perfect symmetry. The Higgs field did something analogous. It fell from its high-energy symmetric state into a stable, non-zero value that now permeates all of space. This single event broke the electroweak symmetry. In that instant, the unified force split in two, giving us the distinct electromagnetic and weak forces we know today. Crucially, three of the particles that mediated the old unified force, the W and Z bosons, became massive by interacting with this now active Higgs field, while the photon, carrier of light, remained massless. This is why the weak force has such a short range, confined to the atomic nucleus, while light can travel across the universe. So the Higgs field did more than give particles mass. It wrote the rule book, deciding which forces would act over what distances. It carved the first fundamental division in nature's forces. But if one field broke symmetry to create two forces, could a deeper, earlier field have united even more? This leads to a grander vision, a hypothetical field from the universe's very first fraction of a second. Physicists call it a grand unified theory field. The dream is breathtaking. Just as the electroweak force split, perhaps the electroweak force and the strong nuclear force were once a single, majestic superforce. At energies so high, they existed only in the first fleeting moments after the Big Bang. Quarks, which feel the strong force, and electrons, which do not, would have been interchangeable. The laws governing them would have been symmetric and unified. A grand unified theory field would have been responsible for this unity. Then, as the universe expanded and cooled past an unimaginable energy threshold, this gut field would have undergone its own symmetry-breaking phase transition. This event would have split the superforce into the distinct strong and electro-weak forces we see today. The implications of such a field are staggering. It could explain deep mysteries like why the electric charge of a proton perfectly balances the charge of an electron. More dramatically, the particles that mediate this unified force, hypothetical entities called X and Y bosons, could have a startling property. They might allow protons, the seemingly permanent building blocks of atoms, to decay. In our current broken symmetry world, protons are stable. But if a grand unified theory is correct, the proton's stability is an illusion born of our low-energy reality. Over inconceivably long timescales, a proton might spontaneously transform, decaying into lighter particles. This means all matter is potentially mortal. While we have never observed a proton decay, massive experiments buried deep underground, like Japan's Super Kamiokande, watch vast tanks of ultra-pure water waiting for a single telltale flash of light from a dying proton. The absence of a signal so far tells us that if a gut field exists, its symmetry-breaking scale is even higher, and its mediating particles even more massive than we once thought. These symmetry-breaking fields are the universe's architects. They are not just components of reality. They are the mechanisms that selected the rules of reality from a menu of possibilities, freezing fundamental constants into place as the cosmos cooled. Each breaking created a new chapter, a new set of laws. And if this pattern holds, it begs a monumental question. Before the first symmetry broke, before even time had meaning, could all of nature's forces have been one, described by a single primordial field? The grand vision of unification leads us to the one force that stubbornly resists being merged. Gravity is the odd one out. While the other forces are described by quantum fields dancing on the stage of space-time, gravity is the stage itself. This brings us to the ninth theory, a perspective that redefines gravity, not as a force field, but as a geometric one. This is the essence of Einstein's general relativity, sometimes called geometrodynamics. The core idea is radical. Picture a taut trampoline. This flat, two-dimensional fabric represents empty space-time. Now, place a heavy bowling ball in the center. The trampoline sags, creating a curved depression. Roll a marble near the edge, and it will spiral inward toward the bowling ball. The marble is not being pulled by a mysterious force. It is simply following the straightest possible path, a geodesic along the curved surface created by the heavier objects present. In our universe, mass and energy do exactly this to the four-dimensional fabric of space-time. The sun creates a curvature. Earth is not pulled by an invisible tether. It is falling freely along the curved geodesic of that solar well, a perpetual fall we experience as orbit. In this view, gravity is not a force transmitted by a particle. It is the geometry of the universe responding to its contents. The mathematics of this are encapsulated in Einstein's field equations, a set of relationships that are beautifully simple in concept but notoriously complex to solve. They state, in essence, that the curvature of space-time on the left side of the equation equals the distribution of mass and energy on the right. Mass tells space-time how to curve. Space-time tells mass how to move. This theory has passed every test with flying colors. It predicted the bending of starlight around the sun, which was confirmed during a solar eclipse. It explains the precise orbit of Mercury and the existence of black holes, regions where space-time curvature becomes infinite. It even predicts ripples in space-time itself, gravitational waves, which we finally detected directly in 2015. Yet for all its success, this geometric field presents the single greatest challenge in modern physics. We cannot quantize it. The other three forces are described by quantum field theory, where forces are mediated by discrete packets of energy called gauge bosons, like photons for electromagnetism. For gravity, the hypothetical mediator is the graviton. But when physicists try to apply the same quantum rules to the gravitational field, to the geometry of space-time itself, the mathematics breaks down into nonsense, producing infinite probabilities. The problem is that general relativity is a classical, smooth theory, while the quantum world is granular and probabilistic. At the extremely tiny scale of the Planck length, a distance a billion trillion times smaller than a proton, space-time itself should be foaming with quantum fluctuations. The smooth trampoline becomes a seething, bubbling quantum foam. In this realm, concepts like before and after, or even here and there, may lose all meaning. This is the heart of the quantum gravity problem. How do we describe the geometry of space-time when that geometry is itself subject to quantum uncertainty? How do we marry the cosmic stage with the quantum actors upon it? The quest for this answer has led to some of the most mind-bending theories in existence, suggesting that the geometric field we call gravity might be an emergent illusion, a holographic projection from a deeper, stranger reality. Gravity as geometry is a breathtaking idea, but what if we have only described half the picture? Einstein's general relativity describes curvature, how mass warps the fabric of space-time like a weight on a mattress. Yet there is another geometric possibility, a hidden twist in the very threads of the cosmos. This is the torsion field. While curvature is a bending or stretching, torsion is a twisting. Imagine not just a depression in that trampoline, but the fabric itself being wrung like a wet towel along the path of a moving object. In mathematical terms, curvature relates to mass and energy, while torsion relates to something more subtle, the intrinsic angular momentum or spin of particles. Every electron, every quark, spins like a tiny top. This is not a particle physically rotating, but a fundamental quantum property as essential as its electric charge. The theory that incorporates this twist is called Einstein-Cartan theory, an extension of general relativity developed in the early 20th century by Einstein and the mathematician Élie Cartan. In this framework, space-time is not just curved by mass, it is also twisted by spin. The density of spinning particles in a region could impart a gentle, corkscrew-like structure to the geometry around them. This opens fascinating doors. One major implication is that torsion could provide an alternative explanation for phenomena we currently attribute to dark matter. In regions like the outer halos of galaxies, where stars orbit faster than visible mass can account for, conventional theory needs invisible dark matter to provide extra gravity. Torsion offers a different solution. The collective spin of countless particles within the galaxy could generate a torsional field that subtly alters the dynamics of space-time itself, creating effects that mimic the gravitational pull of unseen matter. It would not be an extra substance, but an extra property of the geometry generated by what is already there. Another profound connection is between space-time and the quantum world. In Einstein-Cartan theory, torsion is directly sourced by quantum spin. This provides a tantalizing geometric link between the large-scale fabric of the universe and the microscopic spin of its fundamental constituents. It suggests that the quantum property of spin is not just a feature of particles living in space-time, but something that actively sculpts space-time's hidden structure. For a moment, this seems like a perfect bridge between gravity and quantum mechanics. Yet the torsion field remains deeply controversial and purely theoretical. The predicted effects are extraordinarily weak under normal conditions. In most of the universe, the density of matter, and thus the density of spin, is so low that Any torsional twisting would be utterly negligible compared to the effects of curvature. Only in environments of unimaginable density, like the first moments after the Big Bang, or perhaps deep inside a neutron star, might its influence become significant. To date, no experiment or astronomical observation has found conclusive evidence for torsion. It exists as an elegant mathematical possibility on the pages of theoretical physics, a ghost of a twist waiting to be discovered. Its value lies in reminding us that our geometric description of reality may still be incomplete. If space-time can curve, could it also twist, knot, or fold in ways we have not yet conceived? The search for a complete theory often leads us to consider all possible motions of the cosmic stage, not just its bends. The geometry of space-time may be twisted by spin, but could there be a field that shapes life itself? This brings us to one of the most controversial ideas in modern thought, the theory of morphic fields. Proposed by the biologist Rupert Sheldrake, it ventures far beyond mainstream physics into the realm of biology and collective consciousness. Sheldrake's core hypothesis is that the development and behavior of living things are guided by non-material patterns or morphic field. Think of them as invisible blueprints, not made of matter or energy, but of information and habit. A morphic field for an oak tree, for instance, would contain the collective form and growth pattern of every oak that has ever existed. It is a resonant memory of the species. This leads to the idea of morphic resonance, the process by which these patterns are established and strengthened. The more often a particular form or behavior occurs, the more probable it becomes for future members of that species. It is a kind of collective learning across time and space. A famous example Sheldrake uses involves laboratory rats. If rats in one lab learn a new maze, rats of the same breed in another lab, anywhere in the world, should theoretically learn that maze faster, even with no physical connection, because the successful behavior pattern has entered the species' morphic field and become more accessible. This concept extends beyond biology. Sheldrake suggests morphic fields could explain phenomena like the uncanny uniformity of crystal formation or even human cultural habits. It proposes that the universe has a kind of memory and that natural laws are more like habits that have evolved over time. Mainstream science has overwhelmingly rejected this theory. The primary criticism is that it is not falsifiable in a rigorous, testable way and offers no known physical mechanism. It is seen by many as a retreat into mysticism, abandoning the materialist foundations of biology and physics. Sheldrake's experiments attempting to demonstrate morphic resonance, such as those on the speed of learning in animals or human telepathy, have been widely criticized for flawed methodology or an inability to be reliably replicated. Yet, despite its scientific exile, the idea of morphic fields has had a profound cultural impact. It resonates deeply with people's intuitive sense of interconnectedness, with ancient concepts of collective unconscious and with holistic views of nature. It challenges the reductionist view that everything can be explained by atoms and molecules alone, suggesting instead that information and pattern are fundamental forces in their own right. Whether a discarded speculation or a glimpse of a deeper truth, the morphic field theory forces a critical question. Are the forms and behaviors we see in nature solely the product of blind genetics and physics? Or could there be an organizing principle, a field of habit and memory, silently guiding the unfolding of life? The quantum vacuum is not merely a quiet hum, it is a roaring ocean of infinite energy. This is the zero-point field, the ground state of all quantum fields. Remember those virtual particles that blink in and out of existence. Their fleeting dance contributes to an underlying energy that permeates every cubic centimeter of space, a seething background that never turns off. The calculations for its density are straightforward, and they produce a number so catastrophically large it defies belief. According to quantum field theory, the energy in a single cubic centimeter of empty space, smaller than a sugar cube, should be enough to boil all the oceans on Earth. Extrapolate that to the volume of the observable universe, and the result is an energy density over 120 orders of magnitude greater than what we observe in the cosmos. That is a 1 followed by 120 zeros. It is the worst mismatch between theory and observation in the entire history of science. This is the cosmological constant problem. If the vacuum energy from the zero-point field is so unimaginably powerful, why doesn't it cause the universe to tear itself apart in a violent, instantaneous explosion? Why is the actual cosmological constant, the energy of empty space we measure from cosmic acceleration, so infinitesimally small by comparison? It is as if we calculated the pressure at the heart of a star, but when we looked, we found only the gentle warmth of a candle, flame. One haunting possibility is that the zero-point field's titanic energy is real, but almost perfectly cancelled out by some other negative energy contribution we do not yet understand. The fields could be locked in a precarious billionth of a percent balance, leaving behind only the tiny residue we call dark energy. This fine-tuning seems absurd, yet here we are in a stable universe, so an explanation must exist. This immense hidden power has also fueled dreams of revolutionary technology. The concept of zero-point energy as a power source or for propulsion captures the imagination. The most famous and controversial example is the M drive. Proposed in the early 2000s, it was a metallic cone-shaped cavity that, when filled with microwaves, allegedly produced a tiny thrust without expelling any propellant. This violated the conservation of momentum, a cornerstone of physics. Some fringe theorists suggested it might be interacting with the quantum vacuum, pushing against the zero-point field itself, effectively creating thrust from nothing. Mainstream physicists were deeply skeptical, and after years of testing, the consensus is that the measured thrust was likely due to experimental error, such as thermal effects or magnetic interactions with the Earth. The M drive appears to be a dead end. Yet the dream of harnessing the vacuum persists in more credible, though distant forms. The Casimir effect, which we discussed earlier, is a real, measurable force arising from vacuum fluctuations. While not a source of free energy, it demonstrates that the zero-point field can indeed do work, nudging physical objects. Could we ever build an engine that rides these quantum waves? The challenges are monumental, bordering on impossible with our current understanding. The zero-point field is a background state, the lowest energy possible. Extracting usable energy from it would be like trying to get water to flow out of a lake that is already at sea level. You would need a lower place for it to go, a state of even lower energy, which by definition does not exist. So the zero-point field remains the universe's greatest untapped reservoir and its most profound puzzle. It screams with potential energy that our mathematics insists is there, yet our reality calmly ignores. Solving this paradox may require not just a new field, but a whole new way of understanding what energy and emptiness truly are. The zero-point field's staggering energy presents a paradox, but some cosmologists proposed a universe that needed no beginning at all. This was the steady-state theory, a bold challenge to the Big Bang, and it required its own unique hidden field to function. Proposed by Fred Hoyle and later developed with Jayant Narlikar, this was the C field, or creation field. Its purpose was elegant and radical, to continuously create new matter from nothing, maintaining a universe with no start and no end. In the mid-20th century, the dominant cosmological debate was between two visions. One was the evolving universe of the Big Bang, expanding from a hot, dense origin. The other was the steady-state model, which held that the universe, on the largest scales, always looked the same. It had no singular creation. It simply was and always would be. But there was an obvious problem. If the universe is expanding, galaxies are moving apart, so the average density of matter should be decreasing over time. To keep the density constant, new matter must appear to fill the gaps. Enter the C field. Hoyle and Narlikar proposed this scalar field as the engine of continuous creation. It would not create matter in great bursts, but slowly and imperceptibly. The math suggested that as the universe expanded, the C field's energy would be converted into hydrogen atoms, materializing in the vast, empty spaces between galaxies. The rate required was almost undetectably small, roughly 1 atom per cubic meter every few billion years. This was not enough to notice locally, but across the cosmic volume, it would be sufficient to keep the overall density steady for eternity. The universe would be infinite in both time and space, with no need for a dramatic beginning. The C field was a clever fix, but it was more than just a mechanism. It represented a philosophical preference for a universe without a moment of creation, an eternal, self-renewing cosmos. For a time, it was a serious competitor. Then, in the 1960s, the discovery of the cosmic microwave background radiation delivered what seemed a fatal blow. This uniform bath of microwaves was exactly the predicted cooled remnant of the Big Bang's hot, dense phase. The steady-state theory had no natural explanation for it. Hoyle and others tried to salvage the model by suggesting the CMBR was starlight scattered by interstellar dust, but this was ad hoc and unconvincing. With further evidence like the evolution of quasars and the precise black body spectrum of the microwave background, the Big Bang model became the standard and the C field faded into history. Yet it remains a fascinating footnote. It was a serious attempt to use a hidden field to answer a fundamental question about existence itself. Could the universe be self-sustaining? While the evidence strongly points to a dynamic, evolving cosmos with a beginning, the C field reminds us that our answers are shaped by the fields we are willing to imagine. It stands as a testament to scientific creativity, a solution for a universe that, in the end, probably does not exist. Matter and energy may be secondary actors in a deeper cosmic play. What if the most fundamental ingredient of reality is not something you can touch or measure as force, but something you can process? This is the radical proposition of the information field, the idea that the universe is, at its heart, a vast computation. The stuff of stars and atoms might be a manifestation of data. This perspective emerges from the intersection of quantum mechanics, gravity, and computer science, leading to a philosophy often called it from bit, coined by the visionary physicist John Archibald Wheeler. He suggested that every particle, every field, every event ultimately derives its existence from binary answers to yes or no questions. In this view, the cosmos is not a machine made of matter, but a network of information being continuously processed. The laws of physics are not written in stone. They are the algorithms of this cosmic computer. A stunning implication of this comes from black hole physics. When an object falls into a black hole, it seems its information is lost forever, violating a quantum principle that information must be conserved. To resolve this paradox, physicists like Leonard Susskind proposed the holographic principle. It states that all the information describing a three-dimensional volume of space can be encoded on its two-dimensional boundary, like a hologram. For a black hole, the information of everything inside it is not destroyed but smeared across its event horizon, the point of no return. Scale this idea up to the entire universe. The holographic principle suggests that our three-dimensional reality, with all its galaxies and particles, could be a projection from a two-dimensional information field painted on the cosmological horizon, the farthest edge of the observable universe. You, your surroundings, everything you experience, could be a fantastically complex hologram. This is not a metaphor for how the brain works, but a potential physical description of space-time itself. Digital physics takes this further, proposing that the universe is literally discrete, not continuous. Just as a digital image on a screen is made of indivisible pixels, space-time might be composed of fundamental Planck-scale units. In this framework, particles are not tiny balls, but stable patterns of information, like gliders in the cellular automaton game of life, moving across a grid of fundamental bits. The forces between them are not exchanges of other particles, but the result of information exchange rules governing the grid. This shifts our entire ontology. Instead of asking what the universe is made of, we ask what it computes. The information field would be the substrate, the cosmic hard drive, and the unfolding of time is simply the execution of the program. The constants of nature, like the speed of light or the strength of gravity, would be system parameters in the code. This idea is profoundly elegant, but also deeply strange. It suggests that at the smallest scale, reality is chunky and digital, not smooth and analog. It raises the ultimate question. If the universe is a computation, who or what is running the program, and what is the purpose of the output? The idea of a universe built from information leads to a startling question. What processes that data into experience? This brings us to one of the most ancient and debated ideas in philosophy, now finding new life in modern physics, panpsychism. It proposes that consciousness is not an accidental byproduct of complex brains, but a fundamental property of the cosmos, as basic as mass or charge. In this view, consciousness is a field, or a property inherent to all matter. Even an electron, a quark, or a photon possesses a tiny, elemental spark of subjective experience. Not thoughts or feelings, but a raw, minimalist form of awareness, a bare something it is like to be that particle. This seems outlandish at first. We are used to thinking of consciousness as the glowing end product of billions of neurons firing in a biological supercomputer. But this traditional view runs headlong into the hard problem of consciousness, articulated by philosopher David Chalmers. The hard problem asks, why and how does physical processing in the brain give rise to subjective experience? Why does the electrical storm of neural activity feel like the rich, vivid sensation of the color red, the taste of chocolate, or the pang of sadness? Neuroscience can map correlations, showing which brain areas light up during specific experiences, but it cannot explain the leap from objective activity to subjective inner life. Panpsychism offers a radical solution. It suggests consciousness does not emerge from complexity. Instead, it is fundamental, woven into the fabric of reality from the start. Just as gravity is a property of mass and electromagnetism a property of charged particles, experience is a property of matter itself. In this framework, the human mind is not a creator of consciousness, but a collector and unifier of it. Our brain does not generate the light of awareness from darkness. It takes the myriad tiny whispers of experience from the fundamental fields and particles that compose it and integrates them into the single, coherent stream we recognize as ourself. This idea finds intriguing, though speculative, intersections with quantum mechanics. Some interpretations, like those suggested by Roger Penrose, propose that quantum processes in the brain's microtubules are the seat of consciousness. If consciousness is linked to the quantum realm and quantum fields are universal, then perhaps the substrate of experience is too. The appeal of panpsychism is its elegance and its avoidance of magic. It does not require consciousness to pop into existence mysteriously once a system reaches a certain threshold of complexity. Instead, it is always there, just in simpler forms. A rock composed of countless particles with infinitesimal experience, would have no unified consciousness because its components are not integrated in the way a brain integrates signals. But the potential for feeling is still present, diffused throughout its structure. Critics argue this simply pushes the problem back a step. How do these micro-experiences combine? This is the combination problem. How do billions of tiny subjective points coalesce into my single, unified awareness of typing these words? Proponents are working on answers, often using analogies from physics. Many particles combine to create a single gravitational field. Many voices combine into a choir's single chord. Perhaps consciousness works similarly, with integration as a fundamental law of the conscious field. Whether panpsychism is a profound truth or a poetic speculation, it challenges our deepest assumptions. It asks us to consider that the universe is not just alive with quantum fields and information, but awake with an ancient, pervasive form of sentience, waiting to be organized into minds. Time itself may not flow as a smooth river, but as a series of discrete, indivisible moments. This is the theory of the chronon field, a radical proposal that time is not continuous, but quantized. Just as light comes in packets called photons, and energy in quanta, time might have its own fundamental grain, a smallest possible unit known as a chronon. Imagine the universe not as a movie playing on a seamless reel, but as a cosmic flipbook. Each page is a static snapshot of reality, a single frame of space-time. The chronon would be the duration of that single frame. The illusion of smooth motion and flow would arise from the rapid succession of these static moments, just as flipping the pages of a book creates the illusion of animation. The existence of such a field would mean there is a limit to how finely we can slice any interval. There would be a shortest meaningful moment, a temporal pixel below which the concept of before and after loses all meaning. This scale is unimaginably small, likely at the Planck time, which is about 10 to the power of negative 43 seconds. To put that in perspective, there are more Planck times in a single second than there have been seconds since the Big Bang. The implications for physics are profound. A discrete time could resolve some of the most vexing paradoxes at the heart of quantum gravity. Consider the notorious problem of singularities inside black holes, where general relativity predicts that density and curvature become infinite. In a quantized time model, the equations might simply stop making sense before reaching that infinity, because you cannot cram an infinite number of events into a finite number of chronons. The singularity might be smoothed out or replaced by a different kind of boundary. Furthermore, many of the infinities that plague attempts to merge quantum mechanics and gravity arise from calculations that assume space-time is infinitely divisible. If time has a smallest grain, these mathematical pathologies might be naturally cut off, offering a cleaner path to a theory of quantum gravity. Our perception of time's arrow, the one-way direction from past to future, could also find a new explanation. In a flipbook universe, each page is determined by the previous one. The chronology is fixed by the order of the frames. But what determines that order? Some theories suggest the chronon field itself has a preferred direction, a built-in asymmetry that gives us causality. On a practical level, if chronons exist, they would impose an ultimate limit on measurement and computation. No clock could ever tick faster than the chronon rate. No computer could process an operation in less than one fundamental unit of time. This sets a theoretical maximum speed for any possible calculation in our universe. While there is no experimental evidence for chronons yet, the idea challenges our deepest intuitions. We experience time as a smooth, continuous medium. But our senses are coarse instruments built for survival, not for perceiving the universe's finest stitches. The search for a theory of everything may ultimately require us to accept that time, like everything else, is pixelated, a cosmic field ticking to the rhythm of its own elementary beat. If time itself may be quantized, could there be fields that operate entirely outside its normal flow? This brings us to one of the most famous speculative ideas in all of physics, the tachyon field. Tachyons are purely hypothetical particles with one defining, mind-bending property. They must always travel faster than light. In the equations of special relativity, as an object with real mass approaches light speed, its energy requirement soars toward infinity. But if you mathematically plug in a particle with an imaginary mass, a mass that is the square root of a negative number, something flips. The equations suggest such a particle could only exist at speeds greater than light, and slowing down to the speed of light would require infinite energy. It is as if the cosmic speed limit works in reverse for them. This imaginary mass is the signature of the tachyon field. When this field is in a high-energy, unstable state, its excitations are these faster than light tachyons. But here is where it gets truly strange. According to the principles of relativity, a particle moving faster than light, from one perspective, could appear to be moving backward in time from another. This opens the door to all the classic paradoxes, like sending a signal to your own past. Furthermore, in quantum field theory, a tachyon field is not seen as describing real, zippy particles. Instead, it is a red flag in the mathematics, a sign of instability. It indicates that the field is in the wrong state, like a pencil balanced perfectly on its point. The slightest nudge, and it will fall into a stable configuration. This process is called tachyon condensation. The field rapidly rolls down its energy slope to a stable minimum, and in doing so, it undergoes symmetry breaking. The imaginary mass disappears, and the excitations around the new stable state become ordinary, massive particles. This mechanism is actually used in some versions of string theory to describe how the universe settled into its current, stable vacuum state from a more energetic, symmetric beginning. So in serious theoretical physics, tachyons are less about interstellar travel and more about cosmic transitions. Despite this theoretical utility, most physicists consider tachyons as we imagine them, as detectable faster-than-light particles, to be unphysical. Their existence would wreak havoc with causality, making cause and effect impossible to define and allowing information to flow backward in time. No experiment has ever found a hint of them. Yet their allure is undeniable. They have become a permanent staple of science fiction, a convenient plot device for time travel, instant communication, or exotic propulsion. They represent the tantalizing dream of breaking the ultimate barrier, of stepping outside the conventional flow of space-time. While they likely do not exist as tangible particles we could ever catch, the tachyon field concept endures as a powerful mathematical metaphor for instability and change. A ghost in the equations reminding us that the universe's stable laws may have been born from a state that fundamentally could not last. The idea of fields like the tachyon pushes us to the very edge of known physics. But what if the fundamental ingredients of reality are not point particles at all? This leads us to the sweeping vision of string theory, which proposes that at the tiniest scales, everything is composed of vibrating loops of energy, strings. To make this mathematically consistent, the theory requires something extraordinary, extra dimensions of space. Not just the three we experience, but 6 or 7 more, curled up into shapes of breathtaking complexity. These are the Calabi-Yau manifolds. Picture our familiar 3-dimensional space as a vast, flat plane extending in all directions. Now, imagine that at every single point on that plane, attached like an invisible flower, is an unimaginably tiny, 6-dimensional shape. This shape is not a sphere or a cube, but a Calabi-Yau manifold, a twisted, intricate geometry with holes and tunnels, a landscape of hidden dimensions, smaller than a proton. The way a string vibrates is not random. It is constrained by the exact geometry of this tiny, curled-up space. Much like the air vibrating in a flute produces specific notes based on the flute's length and shape. The possible vibrational patterns of the string correspond directly to the properties we observe in particles. One specific resonance might give us an electron with its particular mass and charge. Another might produce a photon, a quark, or even a graviton. In this framework, every particle is a different note on the same cosmic instrument, and the Calabi-Yau manifold is the instrument's design. The geometry determines the physics. Change the shape, even slightly, and you change the vibrational spectrum, which means you change the fundamental constants and particles of that universe. This offers a staggering possibility. The reason our universe has the exact laws it does might simply be because our particular Calabi-Yau manifold settled into a specific shape during the early cosmos. Countless other shapes, and thus countless other sets of physical laws, could exist in a vast multiverse. But strings are not the only actors in this higher dimensional drama. String theory also introduces brains, short for membranes. These are multidimensional objects that can have various numbers of spatial dimensions. A 0 brain is a point, a 1 brain is a string, a 2 brain is a sheet or membrane, and so on. Our entire three-dimensional universe could, in fact, be a 3-brain, a vast floating sheet embedded within a higher dimensional space called the bulk. This is the brain world scenario. In this picture, we are stuck on our brain, like ants living on the surface of a vast leaf, unable to perceive the full depth of the forest around us. All the particles of the standard model, like electrons and photons, could be open strings whose endpoints are pinned to our brain, which is why they, and the forces they mediate, are confined to our 3 spatial dimensions. Gravity, however, could be different. It might be mediated by closed loops of string, which are not tied down. These gravitons could leak off our brain and into the bulk, spreading their influence into the extra dimensions. This could explain why gravity is so astonishingly weak compared to the other forces. It is not weak at its source. It is simply diluted, its strength leaking away into dimensions we cannot see. This idea leads to dramatic possibilities. If another brain floated parallel to ours in the bulk, a collision between them could have been the Big Bang itself, and gravitational waves from events on that other brain might be detectable as whispers in our own. The mathematics of Calabi-Yau shapes and brain worlds are among the most complex ever devised, a landscape of hidden geometry that could contain the blueprint for all of reality. They suggest that what we perceive as fundamental laws are merely the shadows cast by the vibrations of strings dancing in dimensions curled too small for us to see. Einstein's relativity seemed to banish the ether forever, but its ghost has returned in a new quantum form. The original concept, the luminiferous ether, was a 19th century necessity. Physicists knew light was a wave, and waves needed a medium to travel through, like sound needs air. They envisioned the ether as a stationary, invisible, jelly-like substance that filled all of space, through which Earth and the stars moved. The famous Michelson-Morley experiment aimed to detect our planet's motion through this ether wind by measuring subtle changes in the speed of light. They found nothing. Light's speed was constant in every direction, a result that baffled the scientific world until Einstein provided a revolutionary answer in 1905. His theory of special relativity declared that light needed no medium. Space and time themselves were the stage, and the speed of light was an absolute cosmic constant. The mechanical, drag-inducing ether was dead. It was a triumph of elegant mathematics over cumbersome physical models. Yet, a century later, we find ourselves describing the universe with words that sound eerily familiar. We speak of a Higgs field that fills all of space and gives particles mass. We describe a quantum vacuum that is not empty but seething with virtual particles and zero-point energy. We invoke dark energy as a property of space itself. These are not mechanical mediums, but they are unquestionably all-pervading, non-material entities that dictate physical behavior. In a profound philosophical shift, the ether has not been eliminated, it has been upgraded. We traded a tangible, mechanical jelly for an intangible, energetic substrate. The quantum vacuum is the new ether. It is not a substance you can swim through, but a field of potential and activity that defines the rules of the game. When a physicist says an electron acquires mass by interacting with the Higgs field, they are describing a process conceptually similar to an old ether theory, where a particle's properties were determined by its engagement with a cosmic medium. The difference is in the mechanism, not the metaphysics. The modern view is dynamic and relational, built on quantum principles rather than classical mechanics. So while Einstein was right to dismiss the specific, rigid ether of his time, his own general relativity, which describes gravity as the curvature of space-time, and the quantum field theories that followed, have firmly re-established the idea that space is not nothing. It is a something with structure and properties. The ghost of the ether never left, it simply put on a quantum cloak. Even the most stable structures in nature eventually succumb to entropy and decay. But one theoretical construct defies this universal trend. It is called a time crystal, a bizarre new phase of matter that breaks a symmetry we thought was unbreakable. In physics, we have many symmetries. Rotate a sphere, and it looks the same. That is rotational symmetry. Move a perfect crystal lattice one step over in space, and it repeats. That is spatial translation symmetry. But there is also time translation symmetry. In a closed system with no external driving, the laws of physics are the same today, tomorrow, or a billion years from now. Time itself is uniform. A time crystal shatters this fundamental expectation. It is a quantum system that, in its lowest energy ground state, exhibits periodic motion. It forever oscillates, ticks, or flips between configurations, not because it is being powered, but because that is its inherent stable condition. Think of it not as a machine that runs forever, but as a clock that is the very essence of ticking. A normal clock needs a wound spring or a battery. A time crystal is the spring itself, wound by the laws of quantum mechanics. The concept was first proposed by the Nobel laureate Frank Wilczek in 2012. The initial idea of a perpetually rotating quantum system in its ground state faced immediate skepticism, as it seemed to flirt with the forbidden dream of a perpetual motion machine. But a refined understanding emerged. True time crystals are not energy sources. They do not output work. Instead, they are in a state of persistent, non-equilibrium order, a dance locked in time. They achieve this by being periodically driven by an external force, like a laser pulse, but they respond at a different, slower rhythm. If you tap the system twice, it might only complete one full cycle. This subharmonic response is the smoking gun. The first experimental realizations came just a few years later, in 2017, using chains of trapped ions or dense clouds of nitrogen vacancy centers in diamonds. Researchers would hit these quantum systems with a regular pulse of laser light, and the system would magnetically flip, but at half the frequency of the driving pulse. This ticking persisted as long as the experiment ran, resistant to disturbances, a stable beat in the quantum noise. The implications ripple outward. For fundamental physics, time crystals prove that temporal order can be a genuine, robust phase of matter, just like a solid or a superfluid. They are a playground for studying how complex, non-repeating quantum systems behave over immense timescales. For technology, they hint at possibilities for ultra-precise quantum sensors or memory devices that are incredibly resilient to noise, their stable rhythm acting as a perfect timekeeper. But the deepest implication is philosophical. Time crystals demonstrate a form of perpetual change that does not consume energy. They exist in a kind of quantum eternity, a forever now, showing that even in its most quiet state, the universe may not be still. It might be humming with invisible, timeless rhythms, fields of ordered change woven into the fabric of reality itself. Phantom energy is the dark side of quintessence, a field with a truly terrifying property. Its repulsive force does not just push space apart, it grows stronger over time. In cosmology, the strength of dark energy is described by a number called the equation of state parameter, denoted as W. For a simple cosmological constant, W is exactly -1. For normal quintessence, W is slightly greater than -1, meaning its push can weaken. But for phantom energy, W is less than -1. This minuscule mathematical difference spells a cosmic apocalypse of unimaginable violence, the Big Rip. The logic is chilling. As phantom energy drives the expansion of space, more space comes into existence. Because its energy density actually increases as space grows, it creates a runaway feedback loop. The repulsion gets stronger, which expands space faster, which creates more phantom energy, which strengthens the repulsion further. It is a scream of anti-gravity that grows louder forever. The consequence is not a gradual drifting apart. It is a systematic, escalating shredding of reality itself, from the largest scales down to the fabric of atoms. First, the phantom energy's grip would overcome the gravitational glue binding galaxy clusters together. These vast cities of stars would be flung into the ever-darkening void. Next, within individual galaxies, the stars would be torn from their orbits. Our own Milky Way would be stripped apart, its spiral arms dissolving into a cloud of isolated suns. As the acceleration intensifies, the phantom field's influence would reach inside solar systems. Planets would be ripped from their stars. Earth would be hurled away from a rapidly shrinking, dimming sun into the absolute cold and dark. But the horror would not stop there. As the end nears, the phantom energy's repulsive force would surpass the very forces that hold matter together. With the expansion now occurring at scales smaller than a planet, Earth itself would be torn asunder. Mountains, rocks, and dust would explode into nothingness. Finally, in the last fraction of a second, the phantom energy would attack the fundamental bonds of reality. The nuclear force that binds atomic nuclei would be overcome. Every atom in existence would be vaporized. Then, the electromagnetic force holding electrons to atoms would fail. Ultimately, the expansion would reach down to the Planck scale, the theoretical limit of space-time itself. In this final cataclysm, the fabric of space-time would be stretched until it ruptures. The universe would not end in fire or ice, but in a literal tear in the continuum of existence. The timeline for such an event depends on how close W is to -1. If it is only slightly less, the Big Rip might be tens of billions of years in the future. If it is significantly less, our universe's final moment could arrive in a mere few tens of billions of years, a geological blink of an eye. While current observational data from supernovae and the cosmic microwave background still favor a cosmological constant, the error bars have not completely ruled out phantom energy. The universe's fate hangs on the precise value of a single number we are still struggling to measure. Phantom energy represents the ultimate destructive potential of a hidden field, a reminder that the cosmic stage may not just expand, but one day be torn apart from the inside out. Phantom energy envisions a cosmos torn apart by its own fabric, but other hidden fields might be quietly holding it together. The tensor vector scalar field, or TVES, offers a radically different solution to one of astronomy's greatest puzzles, the missing mass in galaxies. Proposed by physicist Jacob Bekenstein, it is a sophisticated attempt to rewrite the laws of gravity without invoking any dark matter at all. The problem it tackles is clear. When we observe spiral galaxies, the stars in their outer regions orbit far too quickly. According to Newton's laws, the visible mass of stars and gas is insufficient to hold these fast-moving stars in their paths. They should fly off into intergalactic space. The mainstream solution is to propose a halo of invisible dark matter surrounding each galaxy, providing the extra gravitational glue. TVIS takes a different path. It suggests our understanding of gravity itself is incomplete, especially in the weak gravity environments found in the outskirts of galaxies. Bekenstein's theory is a relativistic extension of an earlier idea called modified Newtonian dynamics, or MOND. MOND proposed a simple empirical fix. It said that below a certain very low acceleration threshold, gravity stops following Newton's familiar inverse square law and instead falls off more slowly. This tweak could explain galactic rotation curves without dark matter. But MOND was a non-relativistic rule of thumb, incompatible with Einstein's theory of general relativity. TVIS was Bekenstein's ambitious effort to build a complete relativistic theory that would reduce to MOND in the right limits. To do this, he had to introduce not one but three new fields that work alongside the familiar tensor field of general relativity, which describes space-time curvature. First, a vector field, which has a direction like an arrow. Second, a scalar field, which has a magnitude but no direction, like a temperature reading. In TVIS, gravity is not just the curvature of space-time. It is a combined effect of the usual curvature plus the influence of these new vector and scalar fields. Think of it like navigating a boat. In Einstein's view, you are simply following the curvature of the ocean's surface. In TVIS, you are following that curvature, but also feeling the persistent push of a current, the vector field, and the changing density of the water, the scalar field. On Earth or in the solar system, where gravitational accelerations are high, these extra fields have negligible effects, and TVIS reproduces the precise predictions of general relativity. But in the deep suburbs of a galaxy, where the gravitational pull from the central mass becomes incredibly faint, the scalar field activates. It effectively amplifies gravity, providing the extra pull needed to keep those outer stars whirling at their observed speeds, all without any invisible matter. For a time, TVS generated significant excitement as an elegant, field-based alternative to dark matter. It showed that modifying gravity in a consistent way was theoretically possible. However, the theory has faced severe challenges. It struggles to explain observations of colliding galaxy clusters like the Bullet cluster, where the visible matter and the gravitational lensing effect, which maps mass, are clearly separated. This is perfectly explained by dark matter, which would lag behind the colliding gas clouds, but is very difficult for a modified gravity theory like TVIS to account for. Additionally, the cosmic microwave background and the large-scale structure of the universe are exquisitely fit by models, including cold, dark matter. While TVIS may not be the final answer, it stands as a brilliant and serious attempt to solve a cosmic mystery by introducing new fields into the gravitational dance, challenging us to consider whether the missing ingredient in our universe is stuff or simply a flaw in our understanding of space and time. The search for a psychic field, often called the psi field, ventures into territory mainstream science has largely abandoned. This hypothetical medium is proposed to explain phenomena that defy our current understanding of physics and biology: extrasensory perception, telekinesis, precognition, and psychokinesis. The core idea is that consciousness might generate or interact with a subtle, non-physical field that can transmit information or influence matter across space and time, bypassing the known senses. The history of this search is a long and controversial one. stretching from the spiritualist movements of the 19th century to the secret government programs of the Cold War. Organizations like the Rhine Institute at Duke University conducted decades of card-guessing experiments and dice-rolling tests, aiming to find statistical evidence for ESP. Their results often showed small but persistent anomalies, deviations from pure chance that suggested something unexplained might be occurring. Yet this entire field of parapsychology exists under a cloud of intense and often deserved skepticism. The primary criticism is a stark lack of reproducibility. A successful experiment in one lab under one researcher has rarely been reliably duplicated by skeptical outsiders under tightly controlled conditions. The effects, if they exist, appear frustratingly fragile, vanishing under the harsh scrutiny of rigorous double-blind protocols. This elusiveness leads many scientists to dismiss psi research as a combination of poor methodology, statistical flukes, unconscious cueing, and outright fraud. The search for a physical mechanism for a PSI field has been equally elusive. Proposals have ranged from quantum entanglement in the brain to unknown, low-energy electromagnetic radiation, but none have produced a testable, predictive model that fits within the established framework of physics. The very concept challenges foundational principles like causality and the conservation of energy. How could a thought, without any measurable energy output, influence a physical object or receive information from a future event? Despite the overwhelming skepticism, the search quietly continues. The human experience of intuition, coincidence, and unexplained knowing is so pervasive that some researchers argue it demands investigation, even at the risk of professional ridicule. They pursue ever more careful experiments, often focusing on the Ganzfeld procedure, where a participant in sensory deprivation is asked to receive impressions from a distant sender. The debate ultimately hinges on a fundamental question. Are phenomena like ESP merely the artifacts of our brain's pattern-seeking nature, weaving random noise into meaningful stories? Or could they be the faint, unreliable signals of a consciousness field we have not yet learned to measure? The PSI field remains the ultimate outsider theory, a specter at the edges of science, perpetually doubted yet never entirely dispelled. Amidst the search for a theory of everything, a provocative idea emerged from an unexpected corner. Eric Weinstein, a mathematician and economist, proposed a radical framework he calls geometric unity. It stands apart, not just for its claims, but for its journey, bypassing the traditional channels of peer-reviewed publication and igniting a firestorm of debate about who gets to speak for fundamental physics. At its heart, geometric unity suggests that the universe is a 14-dimensional geometric object. In this view, the particles we see and the forces we feel are not primary. They are shadows, projections, or manifestations of the complex, twisting geometry of this higher dimensional shape. Think of it like watching a movie of a 3-dimensional object rotating on a flat, 2-dimensional screen. You see changing shapes and patterns, but they all originate from a single, unified object you cannot fully perceive. Weinstein claims his framework can naturally derive both the standard model of particle physics and Einstein's general relativity from this single geometric starting point, offering a true unification. The details are mathematically dense, invoking concepts like an observer's moment, a 14-dimensional space he calls the observers, and a reinterpretation of how symmetry works. For a non-specialist, the allure is the promise of elegance, a single geometric origin for all of reality's complexity. Yet the controversy surrounding geometric unity is as significant as its content. Weinstein has presented his ideas primarily through long-form podcasts and public lectures, not through the conventional process of submitting a detailed paper to a scientific journal for rigorous peer review. He argues the existing academic system is too broken, too risk-averse, and too gate-kept to properly evaluate a truly disruptive idea. This has created a stark divide. Supporters see a brilliant outsider challenging a stagnant establishment, a modern-day Galileo. They point to historical cases where revolutionary ideas faced initial rejection. Critics, including many professional physicists, argue that without a formal, testable publication, geometric unity remains a collection of intriguing speculations, not a scientific theory. They contend that the peer review process, for all its flaws, is essential for filtering errors and ensuring clarity. The debate has often become heated, focusing less on the intricate mathematics and more on the sociology of science, on questions of authority, communication, and how breakthroughs are supposed to happen. Can a theory be evaluated by the public before it is scrutinized by experts? Does a compelling narrative and geometric intuition carry weight without the formal machinery of predictions and proofs? For now, geometric unity exists in a unique space, a captivating story of a hidden geometric field that is also a mirror, reflecting our deep tensions about how knowledge is discovered and who gets to define reality's rules. While geometric unity argues from the edges of academia, another profound vision of hidden reality came from deep within its halls. David Bohm, a respected quantum physicist and philosopher, looked at the same baffling quantum experiments as his colleagues and saw not just paradox, but a profound message about the nature of existence itself. He proposed that our tangible world of separate objects and events is a kind of projection, a surface ripple. Beneath it lies a deeper, hidden dimension he called the implicate order. The word implicate means enfolded. Think of it as the universe's master recording, where everything that ever was or will be is woven together in an undivided wholeness. What we experience is the explicate order, the unfolded version where things appear separate, localized, and sequential in time. A powerful analogy Bohm used is the hologram. If you take a holographic film and cut it into tiny pieces, any single fragment, when illuminated with laser light, can still reconstruct the entire three-dimensional image, just with less clarity. Each part contains information about the whole. For Bohm, every electron, every galaxy, every moment in time is like one of those fragments. It seems separate, but it encodes and is connected to the totality of the cosmos through the implicate order. This is not a spiritual metaphor alone. Bohm gave it mathematical teeth with his concept of the quantum potential. In standard quantum mechanics, particles are guided by the wave function, which gives probabilities for where they might be found. Bohm's pilot wave theory, developed earlier with Louis de Broglie, took a more definite view. It said particles have real trajectories, but they are guided by an invisible information field, the quantum potential. This field does not push or pull like a force. Instead, it shapes the path of a particle by providing information about its entire environment, instantaneously, no matter the distance. This is the source of non-locality, the spooky action at a distance that Einstein disliked. In Bohm's view, this non-locality is not a weird exception. It is the fundamental clue that we are seeing glimpses of the implicate order at work. The famous double-slit experiment, where a single electron seems to pass through two slits at once, makes sense if the electron is a real particle being guided by a quantum potential that has already unfolded information about the entire experimental setup, including both slits. The particle does not split. Its path is informed by the whole. This leads to a breathtaking philosophical conclusion. Separation is an illusion of the explicate order. At the implicate level, the universe is one unbroken movement. Your consciousness, the tree outside your window, and a distant star are all unfolding from the same fundamental ground. Bohm saw the fragmentation of our world in both physics and society, as a symptom of mistaking the explicit projection for the deeper reality. He argued for a physics of wholeness, where process is more fundamental than particles, and relationship is more fundamental than isolated things. While Bohm's interpretation is not the mainstream view in physics, its influence has been profound, resonating with thinkers in philosophy, psychology, and consciousness studies. It offers a rigorous, scientific language for a universe that is deeply interconnected, where every part whispers the story of the whole, and where the hidden field is not just a component of reality, but its very source. The universe's hidden architecture may be built from particles we have never seen. Among the most compelling candidates for the dark matter that binds galaxies is a ghost known as the neutralino. It is not a single particle, but a mixture, a quantum blend of the superpartners of the photon, the Z boson, and the Higgs boson. This blend gives it the perfect properties for a cosmic specter. It would be stable, not decaying into other particles over cosmic timescales. It would be massive, perhaps dozens or hundreds of times heavier than a proton. And crucially, it would interact only through the weak nuclear force and gravity, making it nearly transparent to ordinary matter. Billions could be streaming through your body every second, leaving no trace. The neutralino is more than a hypothetical particle. It is an excitation, a ripple in its own quantum field that permeates all of space. This neutralino field would be a fundamental component of reality, as universal as the Higgs field, but far more aloof. In the early universe, as everything expanded and cooled, this field would have condensed into a vast, diffuse cloud of neutralinos. Their collective gravity would have provided the scaffolding upon which ordinary matter could gather, seeding the first galaxies and sculpting the cosmic web we see today. They are the invisible skeleton, the hidden mass that dictates the motion of stars without ever touching the light. The hunt for this field signature is a monumental technological challenge. Deep underground, in labs shielded from cosmic rays, detectors filled with ultra-pure liquid xenon wait for the unimaginably rare moment a neutralino might bump into an atomic nucleus, producing a tiny flash of light or a minute charge. In space, telescopes scan for indirect evidence, like the faint gamma rays that could be produced if neutralinos annihilate each other in the dense cores of galaxies. And at particle colliders, scientists hope to manufacture them by concentrating immense energy, creating these shadows of supersymmetry for a fleeting instant. The neutralino represents a beautiful convergence of ideas, a solution to the dark matter puzzle that emerges naturally from a grander theoretical vision. Yet its silence so far is a growing whisper in the data, a reminder that the cosmos may be built from fields even more elusive than we dare to imagine. The neutralino offers a ghostly anchor for our cosmos, but what if our universe is not a singular event, but one page in an endless, colliding library? This is the ekpyrotic universe, a vision where the Big Bang was not a fiery beginning from nothing, but a violent encounter in a higher dimensional space. The name itself comes from the ancient Greek word for conflagration. In this framework, born from string theory, our entire three-dimensional reality is a brain, a vast, floating membrane adrift in a higher dimensional bulk. Parallel to us, just a microscopic distance away in an unseen dimension, floats another brain, another complete universe. For most of eternity, these two worlds drift apart in the bulk, empty, cold, and nearly static. But they are connected by a hidden force field stretching between them like a spring. This field builds potential energy as the brains separate. Eventually, the spring reaches its limit. The attraction overcomes the drift, and the brains begin rushing back toward each other. They move on a collision course through the hidden dimension. The moment of impact is our Big Bang. When the brains smash together, The immense kinetic energy of the collision is converted into a raging firestorm of radiation and matter, flooding our brain and heating it to unimaginable temperatures. This is not an explosion from a point, but a scalding rebirth across the entire surface of our three-dimensional world. From our perspective, trapped within our brain, it looks exactly like a hot, dense, expanding universe from a singular origin. But the true origin was a clash of worlds. This single collision model is stunning, but it gives rise to an even more profound possibility, the cyclic model. Imagine the brains do not just collide once. After the fiery impact, they bounce apart, driven by the energy of the collision itself, moving back into the bulk. The universe on each brain then evolves, expanding and cooling, forming galaxies and stars, just as ours has. But the hidden field between them continues to act. Over trillions of years, as the universe expands and dilutes, the dark energy driving the expansion eventually decays. The repulsion fades, and the attractive force of the interbrown field takes over once more. The brains are pulled together again for another cataclysmic rendezvous. Each collision resets the cosmic clock, wiping the slate almost clean and beginning a new, hot, dense phase, a new universe in an endless cycle. In this view, the Big Bang is not the beginning of time, but a regular, catastrophic phase transition in an eternal cosmic rhythm. It is a universe with no true start and no true end, only an infinite series of expansions and contractions, births and deaths, each triggered by the dynamics of hidden fields on dimensional membranes. This solves some of the same puzzles as inflation, like the uniformity and flatness of the cosmos, but through a completely different mechanism. The smoothness comes from the brains being flat and parallel before the collision. The energy of impact is uniform across their vast surfaces. The cyclic model also offers a potential future. If it is correct, our accelerating expansion will one day cease, reverse, and lead not to a cold, dark eternity or a phantom rip, but to a glorious, fiery rebirth. All the structure we see, every galaxy, every atom, will be dissolved back into the primordial broth, only to be forged anew in the next collision. The universe becomes a phoenix, perpetually rising from its own ashes, driven by the silent tension between worlds we cannot see. The universe may not be governed by chance after all. There is a theory that restores a clear, definite reality to the quantum world, a vision where every particle has a precise location and path at all times. This is the pilot wave theory, also known as the de Broglie-Bohm interpretation. It begins with a simple but radical assertion. The strange probabilities of quantum mechanics are not a fundamental feature of nature. They are a consequence of our ignorance. In this view, particles are real, point-like objects, but they are not alone. Each one is accompanied by and guided by a hidden wave, a pilot wave that fills all of space like an invisible river current. This pilot wave is the quantum potential field, a mathematical entity derived from the famous wave function. The particle does not create the wave. Instead, it is like a surfer, carried along by the shape and motion of a wave it did not make. The wave guides the particle's trajectory with absolute precision. This explains the infamous double-slit experiment in a beautifully intuitive way. In the standard interpretation, a single electron seems to pass through both slits at once as a probability wave, interfering with itself to create the striped pattern on the detector screen. The pilot wave theory tells a different story. Here, a single electron is always a particle. It goes through only one slit, but its guiding pilot wave passes through both. The wave interferes with itself on the far side, creating a complex pattern of ripples and troughs in the quantum potential field. The particle surfing this field is steered by these interference patterns. It is drawn toward the bright bands on the screen and repelled from the dark ones. Fire electrons one by one, and each follows a specific, deterministic path dictated by the pilot wave. Collect thousands of them, and their accumulated landing spots paint the familiar interference pattern, not because of individual randomness, but because of the invisible guidance of the wave. This idea is powerfully satisfying. It banishes the ghostly superposition where a particle is in many places until observed. In the pilot wave universe, everything has a definite state. The catch, and it is a profound one, is non-locality. The quantum potential field is instantaneous and global. The path of a single electron here and now can be influenced by a change in the field on the other side of the universe with no delay. This spooky connection, which Einstein rejected, is built directly into the theory's machinery. It is the price for having real particles with real trajectories. For this reason, and because it adds an extra layer of complexity compared to the standard probabilistic view, pilot wave theory remains a respected but minority interpretation. It is a complete, mathematically consistent alternative that shows us a universe of hidden variables where chance is an illusion and every motion is choreographed by a silent, all-pervasive field of information. The pilot wave guides each particle with perfect certainty. But what if certainty itself is an illusion? Our final theory asks the ultimate question about the nature of reality. Perhaps the universe is not a fundamental entity, but a construct, a simulation running on a computer of inconceivable power. This is the simulation hypothesis, a modern cosmological myth where the laws of physics are not discovered, but programmed. In this view, every hidden field we have explored, from the Higgs to the inflaton, is not a feature of a base reality. They are part of the simulation's elegant code, the algorithms that govern rendering and interaction within the virtual world. The quantum vacuum's zero-point energy could be the background noise of the processor. The puzzling fine-tuning of constants might simply reflect the parameter choices of the programmers. Even the speed of light could be nothing more than a hard-coded processing limit, the maximum clock speed of the cosmic computer. The argument for this idea often begins with a simple, staggering projection. If any civilization ever reaches a technological level where it can run vast, realistic simulations of conscious beings, and if it chooses to run many of them, then the number of simulated minds would quickly dwarf the number of biological ones. Statistically, we are more likely to be among the simulated entities than the original creators. Some scientists point to potential glitches in the matrix, like the seemingly discrete nature of space-time at the Planck scale, which resembles the pixelation of a digital screen. Others note the role of observation in quantum mechanics, where a system seems to settle on a definite state only when measured, almost like a graphics engine that renders detail only when a player looks at it. Yet the arguments against are equally powerful. A simulation complex enough to mimic every quantum fluctuation in every atom of every star in 100 billion galaxies would require computational resources exceeding anything we can conceive, perhaps even violating known physical limits like the Bekenstein bound. More philosophically, if we are in a simulation, then all of science is just reverse engineering someone else's software, and the quest for a fundamental theory becomes an exercise in hacking. Whether a profound possibility or a philosophical dead end, the simulation hypothesis forces a final, humbling reflection. It asks us to consider that the deepest layer of reality might not be a field of energy or information, but a line of code in a cosmic program, and that our entire journey to understand the universe's hidden architecture has been an attempt to read the developer's notes. From the Higgs boson confirmed in a lab to psychic fields lingering at the fringe of science, this journey reveals a universe built on speculation as much as certainty. The sheer diversity of thought is staggering. We have fields that give mass, fields that drive expansion, fields that hide in plain sight, and fields that might encode consciousness itself. Some are backed by equations and evidence, others by intuition and anomaly. Yet they all share a single, driving purpose, the relentless human pursuit of a deeper reality. we are not content with the surface of things. We probe the darkness between stars and the silence within atoms, convinced that something more is waiting to be found. This quest for hidden fields is, at its heart, a search for meaning, for the underlying rules that whisper why anything exists at all. So the next time you look up at the night sky, do not just see the pinpricks of light, see the vast, invisible architecture. Picture the Higgs field giving substance to every photon that reaches your eye. Feel the phantom tension of dark energy stretching the void between galaxies. Wonder if the gravity-bending starlight is just geometry or the echo of a collision between unseen worlds. The cosmos is a story written in fields we are only beginning to read. Which of these 30 hidden layers captures your imagination the most? Let the mystery pull you in and share the theory that changes how you see everything in the comments below. Behind every theory, from the Higgs to the hologram, lies a single unifying thread: the human mind's refusal to accept a universe without reason. We are pattern seekers by nature. We look at the chaos of the night sky and see constellations. We listen to the static of the quantum vacuum and hear the potential for symphonies of explanation. Each of these 31 theories, whether etched in textbook certainty or sketched on the fringe of imagination, is a testament to that same relentless drive. It is the drive to find the hidden order, the elegant equation, the single beautiful idea that makes the bewildering complexity of existence click into place. The physicist seeking a grand unified field and the ancient astronomer naming the gods of the planets were engaged in the same fundamental act, connecting dots across the void to tell a story about where we are. This journey through hidden fields is not just a catalogue of what might be. It is a map of human curiosity itself. Every failed idea, like the steady state's C field, was a necessary step clearing a path. Every controversial proposal, from morphic resonance to geometric unity, challenges the boundaries of the acceptable and forces us to defend what we think we know. And every confirmed discovery, like the ripple in the Higgs field, is a triumph that redefines reality while opening 10 new doors into deeper darkness. This is how understanding grows, not in a straight line, but in a sprawling, contentious, and glorious conversation across generations. We stand on the shoulders of dreamers who dared to imagine fields where others saw only empty space. So as this exploration ends, a final thrilling question remains. Look at this tapestry of possibilities, from the axion's whisper to the brain-world's collision. Which of these hidden fields, which of these silent architects of reality, do you believe will be the next to step out of the shadows and into the light of discovery, forever changing our story of the cosmos?